everyone, and welcome back to the final video of Chapter 7, where we look at linear regression. In this video, we're going to continue to talk about R squared and finalize some things. So remember, a couple key takeaways is that R squared is always between 0% and 100%. And if R squared is 100%, then the line is just a perfect fit, right? There's going to be no scatter around the line. And that would tell us that the standard error of the residuals would have to be 0. All of the variance is accounted for by the model, and none is left in the residuals. Okay, so that's what that means. Usually, this is too good to be true, though, especially when dealing with real-life data. Data from scientific experiments often have an R squared, for example, in the 80 to 90% range, and sometimes higher. On the other hand, data from observational studies, so if you're looking at data, like retrieving data from somewhere and observing, not performing an experiment, or you're gathering data from surveys, it may show relatively weak association because there's a lot of extraneous variables that we might not be aware of, that you can't control, like you can in an experiment. So if that's the case, an R squared of 30% to 50% or even lower might be taken as evidence of a useful model, whereas in statistics, we may look at an R squared of 30% as being not very useful because it's not close to 100%, right? So a lot of the variability cannot be accounted for by X. So the model wouldn't be very useful. R squared is the first thing people look at when doing a regression analysis because it tells us whether the regression model is even worth looking at. Interestingly, the standard deviation of the residuals, remember that's SE, can give us more contextual information about the usefulness of the model by telling us how much scatter there is around the line. Linear regression models may be the most widely used models in statistics because they have everything we would want in a model. 2 easily estimated parameters, a meaningful measure of how well the model fits the data, and the ability to predict new values. And like all models, linear models are only appropriate when we check appropriate assumptions or conditions and they're true, otherwise they're meaningless. Before we start a regression analysis, you want to check the following conditions. So again, make sure you have quantitative variables. You also want to check the straight enough condition, as the book calls it, which just means is the shape of the scatter plot, is the form linear? You want to check the outlier condition. And then also there's another condition called does the plot thicken condition. Basically, you're looking at the spread of the scatter plot, and it should look roughly the same. There shouldn't be any, gaps and little clusters. The spread should be relatively the same, within reason. Okay, after fitting the regression model, make a plot of the residuals and look for any bends that would violate the straight enough condition, any outliers that maybe weren't clear before, a tendency of the residuals to grow or shrink in size as you go from left to right. Okay, so you'll want to check all those things. And I would like you to pause the video for this final example here and then try to work out these problems, and you can unpause when you're ready to go over it. The level of carbon dioxide in the atmosphere has been measured monthly since 1958 at the top of Mauna Loa in Hawaii. The hope is that measurements in the middle of the Pacific will not be influenced by local traffic or industry. A time plot of carbon dioxide levels, parts per million, versus fractional year shows annual cycles and an overall pattern. first of all, what I want to point out to you all is here you have your graph of the fractional year and then the carbon dioxide levels. You also have regression output. So this came from some statistical software package, okay? If you're given this output and you need to find a regression model, you need to look in this section right here. So we're going to first remember that when we write our model, it's y hat equals b0, which is your y-intercept, plus b1, which is the slope, times x. And here, my y, you can see, is CO2, so we put a hat over that. My intercept, it tells me, is negative 2784.68, plus my slope is next to the x, and my x is year. So the slope is 1.57835, which I can't really fit there, so I'm just going to leave it like that, and then year. So that would be your regression model, okay, if you ever have to build one from the output given. But the first question asks us for is, what is the meaning of r squared in this context? So as you can see, r squared is right here. It's 97.6%. So what that means is 97.6% of the variation or variability in y, which is CO2, carbon dioxide, can be accounted for by a linear model over time, which is years. If I need to interpret the slope, I know that my slope is right here. It's next to my x, so the slope is 1.57835. And if I want to interpret that, remember slope is change in y over change in x. So it's the change in CO2 compared to the change in time or year. So what this means is that CO2 levels are increasing because my slope is positive. They're increasing at what rate? At 1.58 parts per million per year. Okay, do my regression assumptions appear to be satisfied? Okay, well, so if you remember, if you'll recall, what do I need to look at? I need two quantitative variables, which I have, year and CO2 level. Is it linear? Well, the scatter plot does not appear to be linear. There is a bend there. And we can see in our residual plot below that that bend is evident. So therefore, no. And the scatter plot appears to be nonlinear. To the right is the plot of the residuals against the predicted values, as I showed you. Okay, so what they do is they take all the predicted. How do they find that? By plugging in each of these x's into the equation, and then they get their predicted. So that's here. And then they subtract the observed minus the predicted to get the residuals. And when it's graphed, we can definitely see a pattern here. So what can you conclude from the plot of residuals? You want to be specific. In what ways does the residual plot indicate deviations from the regression model? So we can definitely see an upward bend, which we do not want. Remember, in a residual plot, you don't want any pattern. It should look very scattered, no obvious patterns. So it shows an upward bend. And also, the residuals show that the increase in carbon dioxide levels is even faster than a linear growth. Okay, and I can see that it increases much sharper than it does if we were to assume a linear growth here, right? Linear would be more like this. This is increasing at a much faster rate, as we can see in the residuals. And we would need a different model to make any predictions, but that's another course. All right, that is the end of the video. I hope you all learned a lot. If you have any questions, please reach out to me, and I hope you have a great rest of your day.